Today, it's my pleasure to introduce our speaker for the second Emeritus Colloquium presentation. It's Joe Nibler. So Professor Nibler got his BS degree from OSU in 1963, doing his undergraduate research with DCS here, and then moved on to UC Berkeley, and he graduated with a PhD in 1966 working with George Pimentel. Did a postdoc with Lynette at Cambridge, and then I believe in 1967 came back to OSU, where he's spent his entire career so far. I mean, I don't believe there's any upcoming moves in the future, but maybe not. I don't know. While he's been here, Joe has collected a variety of awards. I won't read them all, both from OSU and national awards and international awards. I'll just have three. One was the Lloyd Carter Award for Inspirational Teaching. He won the Humboldt Senior Scientist Award. He was a Humboldt Senior Scientist Awardee. And he also won a very prestigious sounding award, the Top Professor Award, which I assume there can only be one. And that was awarded by the OSU Senior Honors Student Society. So with that, I'll turn the floor over to Joe. We're really excited. I believe the title is something to the effect of 50 plus years at OSU, fun in teaching and research. So Joe, we're really happy to have you.
All right, this is the test. Read the middle one here if you can. So, thanks I'm appreciative of this opportunity to come and tell you what the devil I've been doing for 50 years, or a little bit of it anyway. Hard to believe how quickly it flies by the time. And this is the spot we all have come to love so much. It looks almost the same as it did to me 50 years ago. Maybe a little more grungy on the outside. Probably could use a little sandblasting or something on the facade. But I have many happy memories of events in this building, and I want to share a few of those with you today. So, I'm the second one in this series. And my good friend there, Ken Hedberg, and colleague, came and gave a talk last term, and promptly a week later fell and broke his leg, so that's why he's not here. And Derek Thomas, a week later after Ken's talk, he didn't fall, but his wife fell and broke both her legs. And me, I didn't break anything, but I had my gallbladder removed a week later. So I don't know if there's any correlation here, but you might want to be a little careful for the next week or so after this talk. Dara was supposed to give this talk, this second one. I think it was arranged by height or the age or something. I'm the little guy in here. But maybe it's appropriate that it ought to be by tenure here, because I outrank him. I've been here 50 plus years, and there's a mere newcomer at 40 plus years. And if we draw the extrapolation then further down, you're only going to have a few more of these talks to go through. Actually, I'm cheating a little bit on the 50 plus. I was hired here in 1967. That calculates to be 48 years. But I was an undergraduate here. I don't know how to turn it off. I think there's a button over here somewhere. I was an undergraduate for 4 years, so I'm going to count those in the tenure period. And I had a great time as an undergraduate. I had some really great instructors. Hedberg was actually one of them, if you can believe it. And also these two gentlemen, Wendell Slaybaugh and Jack Decius. Slaybaugh had a big impact on me. I came as a freshman. I was going to be a chemical engineer. And I took honors chemistry from Slaybaugh, who was a great teacher. He was really lively, and lots of demonstrations and a lot of fun in the classes and whatnot. And the peers group was a heck of a lot more fun than the peer group in chem engineering, where I was taking drawing, and I couldn't draw a straight line anyway. So I decided maybe chemistry was better for me. So I switched and did some research with sleigh ball early on. It was actually pretty dull. It was on clays and things like this. But later on, I had an opportunity to work with Jack Decius. He had to write a senior thesis when I was here, so I did it with Decius. Decius was sort of a reserved guy, much quieter, but probably one of the most brilliant people that I ever met. He had a way of thinking about complex things that was just amazing. His clarity of thinking was remarkable. And he introduced me to the subject of vibrational spectroscopy, which is basically what I spent my career on. And this prompted me when I went to graduate school then at Berkeley to work with George Pimentel, shown here. He was a famous spectroscopist at the time. And he too was a truly remarkable person. He was one of the most creative people I've ever known. When I was there, we were doing things. I was working in the field of matrix isolation spectroscopy, but they had other students in the group who had developed the first chemical lasers, and they had another group that was making instruments to send to Mars that actually went there. And he just was a very imaginative guy. He also was very prominent. He was deputy director at NSF. He was in the National Academy. Probably would have gotten a Nobel Prize, I think, if he hadn't unfortunately passed away in his early 60s. But he was also fun. And that showed up in many ways in the interactions in research and also in some other areas. He was on our chemistry department softball team, for example. He was shortstop, and I played second base, so he was a lot of fun. And I enjoyed that so much that I played on our chemistry team here up until just a few years ago. A lot of fun. And then this last picture that I show is sort of interesting. When I was at Berkeley, it was during the free speech era. Students were speaking up about various issues, including the Vietnam War and whatnot. And George was involved in that because he was a Senate faculty representative who was charged with talking to Mario Savio and some of the other free speech folks. And this was a big deal at the time. Life magazine came to find out about what was going on with these radicals at Berkeley. And they were interested in Pimentel because he was advising the students and whatnot. So they came to one of our football games there. This was the infrared spectroscopists playing the macromolecules. Those were organic chemists. That's George there. He was pretty fast. And that's me over there in the corner up there trying to fend off this macro guy over here. He's a 300-pound lineman, I think. And we didn't quite do that well. We lost the game. It was 14-16. We always blame George for that because Life said he was 42 and fast, if you can read this. And we always said, well, maybe, but that day he was 42 and sort of half fast. So you could tease George that way. He was a great teacher, too. Sort of was a little bit of an inspiration to me. He taught freshman chemistry, a full range of courses, was very effective at it. And that's one of the themes that I wanted to stress in this talk. There's fun in all aspects of a career like many of us share. And not the least of this is the fun in the teaching part. And I've always liked it because of a number of reasons, not the least of which, if you try to teach something, you quickly discover how little you know about the subject. And so it's a great way to improve your knowledge on a subject. And of course, if you have to explain things, you sort of improve your communication skills as part of that. But the biggest part for me was always the personal part, the interaction with the students, the opportunity to get to know them and see the development, which is extremely satisfying, both at the undergraduate and the graduate level. At the undergraduate level, I taught all the courses, freshman chemistry and BChem and integrated lab and whatnot, and enjoyed all of them. The freshman chemistry I taught with Margie Hack for a number of years, and in the fall, that was perfect because you get all these really bright, this was the honors course, students coming in, all gaga about what's going on, and so it's a lot of fun to tease them and play a role in their initial start at OSU. And then in the integrated lab, it was nice because you really got one-on-one interaction with students, and that developed for me an interest in laboratory experiments that carried over, for example, in this textbook that I co-authored with some other people. This is still going. Last year was the 9th edition that came out, and we've added to it over the years, and the people in the integrated lab played a major role in some of the development of new experiments, for example. One is shown on the cover here. This is something Casey Coulter-Park did a few years ago, an undergrad here. It's the unfolding of a protein, lysozyme here, which you can monitor optically by looking at absorption or emission. Or you can do it thermally from a differential scanning calorimetry experiment. And Casey did some of the initial work on that. So that was a lot of fun. And then, of course, working with graduates is maybe the optimum case where you have a lot of really close interaction. Research is a shared endeavor, and so you really get to know people, both the good and the bad aspects in the course of this, because research never always goes perfectly smoothly, and you learn to deal with the frustrations and whatnot. So I want to tell you for the rest of the talk mainly about the research and some of the grad students that did this research and the interactions that we had over the years. So I'll do it by decades, a few examples in each. Well, this is the first group of students in '73. They're clowning around here. We were doing infrared matrix isolation spectroscopy at that time. And when I first came to OSU, we hardly had anything in the lab. So we had to write proposals. Jack Decius and I wrote a proposal to get this wonderful dispersive infrared instrument here. It cost a small fortune. It was the Cadillac of instruments at the time. Had a turret with 7 gratings that would rotate, and filters that would rotate into place, and lots of knobs and dials. And students are showing me here how they're going to fine-tune this instrument. Anyway, we used it with this apparatus over here doing matrix isolation experiments. This is a closed cycle helium cooler, so we could get a surface really cold. Matrix isolation means you trap something in a frozen film of argon or some other inert gas so that it doesn't move around, doesn't react, you can stabilize it. And so we were trying to do a number of things, make some novel molecules at the time. Some are listed here. Some we succeeded on, some we did not. The purpose was to get vibrational spectra from these, and it was a pretty simple-minded kind of research, because in almost all these cases there was a structural question. Are they band or linear, or what's the shape of cyclobutadiene, for example? And I'll illustrate this by showing you some data for just the last one here, praseodymium trifluoride and lanthanum trifluoride. We got interested in this because of another of my colleagues, Carol DeCock, who was an inorganic chemist who had done some work on these using infrared matrix isolation methods. And the idea is illustrated here. You have you have a high temperature oven spraying out the metal trifluoride mixed with gas collected on a cold surface, about 20 Kelvin here. That was rotatable, so the infrared could come in, bounce off, and if you rotated it at the right angles, over here was a spectrometer. You could get spectra like the ones that are shown here. And in this case, the question was pretty simple. These molecules are either flat or they're pyramidal. If they're flat, they're planar, then 3 of the 4 vibrational modes ought to be infrared active, like nu3, nu2, and nu4. But the symmetric stretch is not infrared active. If it's pyramidal, though, that would be infrared active. So this one doesn't show anything in that region. It's planar. This one seemed to show something that's pyramidal. Very simple test of structure. And there was only one little problem with this. These same molecules had been looked at Bell Labs and at Harvard by some people who were doing electric deflection experiments. Those test whether you have a dipole moment in the molecule. Well, this has no dipole, and this would have no dipole, and this would. So this one ought to deflect, and this one shouldn't. They got exactly the opposite conclusion on both of these. So that was a puzzle. And the question was, well, is this maybe not nu1, the symmetric stretch? And that's where our research came in. We were trying to extend the matrix isolation methods to develop Raman spectroscopy for this purpose. That had never been done before this. And in the Raman experiment, the strongest band by far for all molecules is always the symmetric stretch. And so we did a Raman matrix experiment. It took a couple of years. We had to get another spectrometer and get some lasers. First lasers at OSU, actually. And this cube up here shows the cold surface there and the laser going up. It's a krypton ion laser. So we just sent a laser in and bounced it over here for the spectrometer. So the same setup could be used for both experiments. And sure enough, we could see in the Raman, I think this is the symmetric stretch. It was quite prominent. And it was a different frequency than what had been assigned here. And here it occurred, and there was a little teeny bit in the infrared. So the point of this was, this reversed the conclusions that you get just from the Raman spectrum itself, and made everything compatible with the electric deflection experiments. So a nice, simple kind of application of spectroscopy, which made Mike Lasecki, the student who was working on this, very happy, because then he could finish his PhD, which he did. And the other students weren't quite as happy. They were working on more challenging problems, and so I had to resort to extreme measures to keep them slaving away. But eventually, these fellows, Doug Coe, shown on the top, Hossein Rajanalab, and Ed Suzuki, all finished up. Doug went on to Montana Tech, where he's Dean of Science now. Hossein was Iranian. He went back to Iran to the University of Tehran, set up a lab, and then about a year later, the Shah was overthrown, and he lost his job because he was a little too liberal. So he managed to get out of the country and spend his career at Intel Labs. And Ed Suzuki went to Seattle, joined the Washington State Police as a forensic scientist, and he's chief scientist there now. He's written several textbooks on spectroscopic applications in forensic science. So we did work that first decade or so in the area of matrix isolation, trying to use Raman spectroscopy with some success, but it's pretty hard because Raman signals are intrinsically very weak. And about 1975, there was a paper that appeared from a group at the Naval Research Labs, which suggested another way of getting Raman information, this method called CARS, coherent Anti-Stokes Raman scattering. And the idea here is you send not just a green beam in, look at scattered light, but you add another laser, tunable, and you tune it such that the beat frequency between the two lasers matches a molecular resonance in the molecule, a vibration, say. And when you do that, it couples the radiation field with the molecule pretty effectively, and you can move energy back and forth. You can take energy from the molecule, add it to a green beam, and make a blue beam out of this. And this is all done in a coherent fashion as opposed to incoherent, meaning it's a laser beam that comes out. Its intensity is given by the sum of amplitudes squared versus, for ordinary Raman, sum of amplitudes squared. So here you sum all the amplitudes and then square. So if you have 1,000,000 photons, you get a signal of 1,000,000 here. Over here you get 1,000,000 times 1,000,000. So gaining 1,000,000 seemed like a pretty good idea. So I decided to go to the Naval Research Labs and arranged a sabbatical there. And they had tons of money, so we were able to build a pretty good apparatus and do a number of experiments, one of which is shown here, which illustrates the power of the method. This is an electric discharge in a gas, nitrogen. It's extremely bright, and there are laser beams going all over the place, so it's a really bright, glaring system. You could normally never do any kind of spectroscopy here because of the background radiation. But because this signal is a laser beam, we could send it through a little hole, an aperture, and that little blue dot you see there is the signal being projected into the camera lens. So it was bright enough that you could actually see it with your eye. And that allowed us to get pretty good data on, in this case, is nitrogen. If you just had a cell without a discharge, you'd only get this first peak. That's the vibrational transition for nitrogen, the so-called Q branch for nitrogen. In the discharge, though, we saw a little bit of this and this. These are for higher vibrational levels in the molecule. So there was V equal 1, 2, 3, 4, 5, 6. We could even see out to the 7th level, which was pretty amazing. There was no other method to get this sort of detail out of such a hostile environment of plasma. And you could poke around in the plasma itself because it was a point probing experiment. So there was a lot of interest in this method as a result of this. People particularly used it to study flames and combustion systems. All the car manufacturers put glass ports on their cylinder walls so they could send these beams in and study the combustion to try to improve efficiency, for example. And there were jet engine studies, all sorts of things. Well, while I was at NRL, I had a grant from NSF to do the matrix work, and they asked me to come and talk about what I'd been doing, and I was pretty nervous, so I went and told them. And then I showed them some of the stuff we'd done at NRL with this CARS method, and then I asked them, and I'm thinking about in continuing this, I'd sort of like to switch over to this CARS method a little bit. And by the way, I'll need about $100,000 for lasers and other gear. And they said, well, we'll think about that. And a couple of days later, they called me and told me, okay, go ahead. So that was great. When I returned to OSU then, we set up a CARS lab. We could buy a laser, a neodymium laser, that's this thing here, but we couldn't buy dye lasers at that time. They didn't exist. So we had to build them. We made them in the machine shop down here. This is Dennis Guthel's working on, that one's getting up. I'm going to switch over to new and improved color here. Okay. And it was good we did this because we learned a lot about optics and lasers and whatnot as a consequence. Dennis subsequently went to work for Rockwell, and he actually wound up working on lasers to shoot down missiles and things of that sort. Ken Gross and John Wilkerson were postdocs in the group at the time. So we built this, And we started to apply it to a variety of different systems, including a little more work on discharges and some molecular spectroscopy. We wanted to look at things that had short lives, like methyl radical, for example, and we still had an interest in that. And one of the projects involved trying to use this method to look at really low densities in molecular beams, something that had not been done at all prior to this effort. And we wanted to look at small molecules. We were mainly interested in seeing if we could look at clusters in these beams, small van der Waals type complexes. That was a hot topic at the time. So this was our first effort in this. This is Peter Huber-Veltley, who was a postdoc with me then. Peter was from Switzerland, from the ETH, where, of course, everything is done in the most elegant way by the Swiss. And so when I told him, well, let's see if we can do molecular beam experiments, he said, oh, great, we'll build a molecular beam apparatus. And of course, he had this vision of a huge thing with all stainless steel or gold plating, and would have taken a couple of years to build. And I said, well, why don't we try something simpler first? And we had a little cube and a pipe here, which we hooked up to a roughing pump. Very simple, crude thing. This is a fuel injector out of a BMW or something like that. The BMW was a little expensive, but the fuel injector was great. And then the laser beams would cross here. So this would puff the gas out into a vacuum chamber, is the idea. And if you just put nitrogen in here, about a torr, and take a spectrum, this is what you get. You get that vibrational frequency, this lump, with some rotational structure, which now we have better resolution than at NRL, so we can see it. And then if you turned on the pump and looked in this close to the nozzle, all the rotational structure disappeared, the line narrowed. And we could calculate the temperatures in each case. It was room temperature here. This was about 35 Kelvin. So this was the very first molecular beam experiment involving any kind of a Raman measurement. And it was lucky that we did this in a sloppy way, because I learned later that there was a guy, Bob Beyer at Stanford, who was a physicist, who was trying to do the same thing, but they wanted to build a fancy apparatus, which took them about a year or so. So sometimes it's better to be sloppy and fast than neat and tidy and furled. So this might be the case like that. So then we went on to apply this. These are some of the students who were in the lab at the time. And I'm showing this because of Margie here. That's Margie in 1983. And Margie spent a little time in the lab. She didn't work on the cars part. She did some matrix experiments with Steve Baird, shown over here. I'm going to actually talk, though, about some of the work George Pubans did with CO2 clusters. George went on to Tektronix labs for his subsequent career. And this is an experiment George did. This is a close-up of the nozzle right here itself, puffing gas out. And if you, this is a CO2, and we're looking at the symmetric stretch right here. And if you just puff the gas out, or if you look at room temperature static samples, all you see is this lump right here, this big, strong spike. And if you look in the jet, but you run the nozzle at room temperature, that's almost all you get. There's a little jump in here, sort of like noise. But if you cool the nozzle, if we can cool this down, if you cool it about 40 degrees K, then we can see this streak of light where the lasers were crossing in front of the beam. You don't see it otherwise. And that indicated something exciting was happening. And well, it's no great surprise if you squirt a CO2 cylinder, you know, you get dry ice coming out of it. So we figured it was just dry ice. Well, this is where dry ice has its feature. We called it polymer. But there's nothing in between in dry ice or in the gas. So these little lumps in here were definitely new things that were being formed in the expansion. And we speculated that maybe this lump here could be the dimer because that was the first thing that formed. And there was interest in these kinds of van der Waals molecules because of the ways in which you might arrange them. For example, here the bonding would be dipole-dipole kind of bond-dipole coupling, whereas here it's more of a quadrupolar kind of interaction. And it turns out from later studies, this one is the more energetic form, or the more favored form. So we published this and some other work, other molecules that form clusters like HCN and acetylene. We were a little disappointed though because we wanted to see fine detail in these spectra, and these were sort of lumpy things. And part of the problem was resolution of our lasers, which was about half a wave number. So that prompted us to try to improve that a little bit. And that was the basis for work for about 20 years after that. Really high resolution CARS measurements, all based on some pretty fancy lasers that were exceedingly narrow in line width. We managed to get funding from the Air Force to buy this equipment and do these studies. The Air Force, it flies up in the upper atmosphere where some of these small clusters are thought to occur. So they wanted to know what their planes were hitting and also what kind of absorptions and spectral properties they had. So they were generous in giving us a fair bit of money for this purpose. So these two set up the lab, George and Mark Marincelli, who's at Penn State now. Just there. And I'll talk about, just briefly, the work of another fellow, Rainer Beck, a German who came and got his PhD here. Amazing guy, really one of the brightest students I ever had. He's a professor in Switzerland at the University of Lausanne. Rainer used the apparatus. This is now again nitrogen we're looking at here. And what we saw was before in the nitrogen vibrational region here, we had just a lump or maybe just a little bit of rotational structure. Now everything is completely resolved, every line here. These correspond to different J values for rotational excitation. And the signal to noise was dramatically improved. Everything was much better. This is in a static cell. If you look in a jet, things collapse, they get cold. It's about 27 Kelvin. You can use this information to reduce the temperature and other properties. We didn't see anything else until we cooled the nozzle. Instead of having the nozzle at room temperature, we started out cold. And in that case, actually, we didn't get as cold in the jet, meaning something was heating up the gas, and that something was the heat of condensation. And we formed something over here, a lump that Rainer studied and managed to extract his PhD out of. This is what he did. He looked as a function of distance out in the Mach disk that you get from a free-flowing jet like this. And what he saw was the line, this red line, shifted to lower wave number values. And then it split and it turned green and it went the other way. And so what Rainer then subsequently showed by looking at an equilibrium static sample was you get precisely that behavior in the liquid when you cool it over these ranges. And then when it freezes to the beta form for solid nitrogen at about 60, the shift goes the other direction. And in fact, if you really get it cold, you can form an alpha solid here. We didn't see that in the expansions because eventually the gas goes out and hits walls and bounces back, so you get a shock boundary here. And once you go through that, then the gas warms up, things would melt. And so we could see gas out here, but it was cold gas. So we never ever saw the solid. But this was pretty new, and I was amazed that we could see a phase transition in these clusters because this total time was in the microsecond range for this flow here. And not only did we see this in the case of nitrogen, but we looked at other molecules. This is a case of acetylene expansions, work done by Kyung Lee and Phil Maneri. Kyung's a professor in South Korea now. Phil went to work for Northrop. And that what they showed was not only could you form liquid, but you could form two solid phases as this cluster flew along. They did this by doing the corresponding cryostat experiments, liquid, cubic solid, and orthorhombic solid. And if you do both experiments, you can, if you assume the cluster is big enough to have bulk-like properties, then you can map from the temperature variation of the frequency, you can go backwards and deduce a temperature in the jet. And so that gave us cooling curves that we could examine as we moved out in the expansion in units of the nozzle diameter. And in the case of acetylene, then it initially formed liquid, and then there was a zone where it froze, and then the cubic solid would go out, and it would cool further because there was some evaporation and inelastic collisions. Initially, there was some condensation. So you could model this, a very simple model, using heat capacities and vapor pressures and whatnot. And the cooling depends upon the size. So depending upon the diameter of the molecule, you could reproduce the observation. And these clusters were huge. They were about 6 microns in diameter. So they clearly had bulk-like properties. We were interested in smaller clusters. And it turns out if you add helium, if you don't use pure acetylene like we did here, then things get much smaller, and we could get clusters down into the nanometer range. So these were some of the very first nanometer studies of molecules in a rather esoteric environment in a pre-jet, in the flowing system. This was in the 80s, I think, in that time period. I'll mention one other experiment that we did. I had a long-term interest in methyl radical from our early matrix experiments, and we finally were successful in getting Raman spectra of the methyl radical shown here. If you take, this is methyl iodide, and if you take methyl iodide by itself, you get a spectrum of strong CH stretching feature here, and nothing else really. But if you then have, this is all in a jet, you pulse out the gas, and you take a UV laser that's pulsed and you blow the molecule apart, it dissociates, photodissociates like this. And if you look fast enough with these pulse lasers, then we can see this molecule just as it's born, as the bond is breaking. And this is what it looks like. This is its spectrum for the CH stretch. And it's actually fairly complicated. There are a lot of features in here. And part of the interest was what are these? Well, it turns out this methyl radical, if it's isolated, it wants to be flat. That's a stable structure. But it's born bent. It's pyramidal because it's methyl iodide. So when this bond snaps, the molecule is excited in its bending mode, the umbrella mode for this molecule. And so this structure that we see here is attributable to excitation of some of the vibrational modes of the molecule. And we were able to map it out and reproduce this spectrum quite nicely. What it gave was pretty detailed information about the initial photofragment in the case of the methyl radical, in addition to some information about the CH stretching frequency and the bond length. This was work by Mansour Zahidi and Nancy Triggs. Mansour is Iranian. He went back to Iran after the Shah was overthrown, and he's a professor at the University of Tehran now. Nancy teaches at a college in Rhode Island, and they were both a lot of fun. One of the activities that I've enjoyed over the years is water skiing, and so one of the things we would always do in my group, I'd drag them off to the lakes in the summer whenever it was a hot day without much resistance. And so we would go and water ski. And Nancy was very good at this. And when she came back and went through graduation, she decided she wanted to get a picture of her in her graduation gown, water skiing across Foster Reservoir. So we tried it. This is a dock, and she hadn't done a dock start before, and so it didn't really work out so well. So I won't show you the after picture. Eventually she got up, and we did get a picture, but the gown was pretty soft and wet by the time. And these are some pictures of some of the other students. It used to be a joke. If you wanted to get a master's degree in my group, you had to get up on at least 2 skis. And if you wanted a PhD, then you had to get up on either a slalom ski or a wakeboard. And most of them managed to do that. Darren was a really interesting guy. He was from Texas. I don't know if all Texans are like Darren, but he was really imaginative, and you never quite knew what he was going to do. This is him. He appeared at our door one Halloween Eve with his wife in these garbs, which I always thought was pretty funny. And we would go to meetings in California. There was a place called the Silmar every year, the Western Spectroscopy Association. And students would either give a talk or give posters. One year I went, and somebody came up to me and said, "You better go check on your students in the poster session." So I went over, and Darren and Phil Manerick were sitting by the entrance with a sign like this. It says, "We'll do nonlinear spectroscopy for food." And another time, he and another guy, they had posters. They put one up, and it was just, they just stuck it up on one of the blank areas and said, "Cars spectroscopy cures cancer." And then they had a picture of a cell with lasers shining on it and all sorts of things. So you never quite knew what you were going to get with Darren. He went back to Texas. He teaches at Sam Houston University now. And I'm sure he's a great teacher because he's a lively guy. Well, I'm getting near the end here. The last decade, we continued on with some of the high resolution spectroscopy, and then something new came in because computers got a lot more powerful, programs got better, and so we started using quantum theory more and more, particularly at the anharmonic level, which is a little unusual. That means instead of just measuring equilibrium positions where the atoms are, you measure not only the curvature, which tells you vibrational frequencies, but higher order terms, cubic terms and quartic terms. That's the anharmonic part of it. Turns out that added information shows up in some of the details in spectroscopy. So there's a nice link between the two. And we made a number of odd molecules. 2 are shown here, and I'll just tell you a little bit about these. The first one is carbon suboxide. This is a linear molecule studied by Tony Masiello and Mark Abel. Mark was an undergrad, went to Berkeley. He works for Intel now. Tony teaches at Eastern Washington University. And we were interested in this because, you know, it's got double bonds between all the atoms, so you'd think it'd be like a rod or something, but it has an amazingly low bending frequency, 18 wave numbers. That's one of the lowest frequencies I've ever heard of. And so it's got unusual properties. We wanted to get spectra for it. We had to make it. And so this is our total synthesis of C3O2. Organic chemists talk about total synthesis of erythromycin or Taxol. Well, here we have a one-step process. We took a pot, put some of this malic acid in with potassium pentoxide and heated. And out sublimes the carbon suboxide. So we made some of this, and because of the low frequency bending mode, a lot of the molecules aren't in the ground state. So we wanted it cold, so we did it in a jet, and this is about 110 Kelvin where we're probing. And what you see is features that come from different vibrational modes here, different populations. And the extra structure is rotational structure, which we could analyze and learn something about the bond lengths and things of that sort. Theory came in here too. We were doing calculations at the highest level we could. And what's interesting is the calculations showed that the molecule isn't linear. It's bent. The equilibrium structure is bent around here by about 150 degrees. But the barrier to linearity, this is really a double minimum because you can bend it up or you can bend it down. The barrier is only 20 wave numbers, and that's about where the ground state level is. So really, in the ground state level, where the molecule really lives, or in higher levels, it's linear. It's a time average over the two double minimum. And so this information here allowed us to map out this n-harmonic potential and learn something about the properties. This kind of a molecule is now turned quasi-linear because it's like it has a wet noodle or something in the middle here. It's just flopping around. The other molecule I consider to be one of the most amazing creatures of all. Amazing because there's a real bond here between these two terminal carbons. And this has no excuse for existence. All four bonds here are on the same side of the carbon. There's nothing out on the top or out on the bottom. This really shouldn't exist, but it does, and you can make it. And we wanted to study its spectroscopy, both cars, and we wanted to get infrared data for this too. There's no instrument at OSU that really does high resolution infrared measurements. But there is at PNNL in Richland. And so we formed a collaboration with these two folks there that's been pretty profitable. What they have that's unique is this $1 million FTIR spectrometer. You know, most FTIRs that we use in the lab, the mirrors, one of the mirrors moves. It moves maybe a centimeter or a few centimeters at most. This thing goes 6 meters. And the further it goes, the higher the resolution of the measurement. So this had about 1,000th of a wave number capability, something that we were interested in using. So we had to make it. Well, we couldn't do a one-pot synthesis of this. It's quite a bit more involved. And we were lucky there because the white group, Jim and his students, were very generous in helping us with some of the steps in this, particularly Keith Schwartz, who now teaches at Portland State University. And so we were able to make some of this, and these are some spectra obtained. These are infrared, taken at PNNL. This center peak here is the vibration in a particular region for a bending mode. And then each of these stacks here corresponds to one more unit of rotational angular momentum. And then there's some extra structure. If you take one of these and blow it up, you see a lot more lines, and those correspond to spinning around the symmetry axis. So there's a K quantum number that's involved. And all of this makes heavy use of quantum theory, and we can understand it, and we were able to reproduce these spectra. There are 1 million lines, and it's really quite detailed, a lot of work sorting through it. But the beauty of it is that you can understand every little feature in here, and from that you get measurement of molecular parameters to unprecedented kinds of accuracy. In this case, the rotational constants about the C is about the symmetry axis and V is about one of the other axes, are really quite well determined. And so we could get those. From that you get this bond length, the odd bond length. And it's a real single bond. It's 1.58 angstroms. The other carbon-carbon single bonds are 1.52 angstroms. So it's only a little bit longer than the other carbons. But beyond this, we wanted to see how well theory worked. And it works pretty darn well. Within 1%, we could get these same parameters. Not, of course, to the accuracy that we measured them, but really quite close. And the new part of this, the anharmonic part, came into play because from our measurements, we not only measured rotational constants, but when a molecule rotates, the bonds extend a little bit. There's a little centrifugal distortion. And you can measure that. That's what these parameters are. They're small, 1,000,000 times smaller for these Ds, 1,000,000,000,000 times smaller for the next higher order corrections. And yet we could measure them to remarkable accuracy from the analysis of these spectra. And the new feature from theory was if you can compute anharmonic terms in the potential, then you can calculate these parameters just as well. And I was blown away when I saw that even these fine parameters could be predicted very accurately from the quantum theory that we can do these days. If you go to the even higher order, you don't do quite as well, but all the signs are right, the magnitudes are right. And of course, this is just for the ground state. We measure these kinds of parameters for all the different vibrational levels. We can compute them there. And so this gives sort of a new kind of test of quantum theory. You can use not just structure, but these other finer parameters to serve as a test of the quality of wave functions and the methods of calculation. And so that's some of what we're trying to do with other molecules. And to finish, these are some. We've made all of these now. We is me and undergrads, one of whom just came in the room here. That's Blake Erickson, who's working in my lab right now to make a deuterated form of this spiropentane. Did you make any today? Yeah. So anyway, these aren't so easy to make. We've been lucky. Jim White's group has helped us for a while, but his lab's closed down now. So we're looking around for other help for these and some other molecules that we want to synthesize. And I'll mention here another interesting structural question on a boral hydride compound that Maha Algambi worked on in my lab. And she's also working with Wei Tong. She did her master's thesis. So we're having a lot of fun with molecules of this sort. And I guess I'm going to close here, and I'll mention the funding agencies over the years. NSF particularly has funded most of the things that we've done over the years, but more recently Dreyfus has funded all of the undergrads that have worked in my lab. And I want to thank all of you for coming to this talk, and the chemistry department at OSU for letting me play around for half a century here. So thank you.
Okay, so we have a couple minutes for questions.
Is there a minimum batting average to graduate school?
A minimum what?
Batting average.
Oh, yeah, we used to have that. It was 300 was the minimum.
Isn't propellant explosive?
Propelling is well, you have to handle it carefully. It'll polymerize if the pressure gets too high. And that was a real question. Could you even do gas phase spectroscopy on this? What we discovered was we could make it. If we kept it cold, it was stable. And if we put it in a cell, as long as we didn't go above 5 torr, we could keep it for a month.
Wow.
And in fact, to make these measurements at PNNL, to move a mirror 6 meters takes a while. They move it very slowly, very precisely. So typically, spectral measurements are over days, and we would fill a long path cell. It was a multiple reflection cell, about a meter, and then you'd have maybe 200 times that. So it's extremely sensitive measurements at low pressures. And it's hardly showed any decomposition at all. So, same was true of another, the radialing, which was take benzene and form a triangle in the middle, cyclopropane, and then double bonds off each corner. That's extremely reactive too. But if you keep the pressure low, you can do measurements of this type. So, yeah, right.
Question about the first set of molecules you looked at, the PRF3.
Yeah.
And you said when they do electrostatic reflection is pyramidal, and then the first type of spectroscopy was planar?
Yeah, the first infrared measurements were interpreted to be such that they were exactly the opposite of the electric deflection experiments. That is, if it's planar, you don't have any deflection. If it's pyramidal, you do. You have a dipole moment. And the arguments were based on the selection rules, the infrared selection rules. And the Raman measurements were key in showing that the interpretation of the infrared was incorrect. So everything was then consistent. Yeah.
What's the misalignment you can get out of a laser now?
Oh,
Because you showed sense of the wave
oh
number
yeah.
is-
Well,
is-
the basic laser that we used, the CW laser, had a line width of about a millionth of a wave number. And currently, I mean, the very best you can do, like at the Boulder Labs at NIST in Colorado, they talk about line widths of a hertz, 1 hertz or less, for short periods anyway. So you can get exceedingly narrow line widths. And that's the basis, you know, for some of these clocks and things like that, where they measure the line widths to the frequencies to really high precision, because they measure them to many hertz.
So why wouldn't you use a laser for observation?
Why wouldn't we go further than we did? Because we're looking at gases, and gases move. There's this thing called the Doppler effect, and it isn't just a shift, because some gases go this way and some go that way. You have a distribution. So you're limited intrinsically by the Doppler width. So there was little, we went as far as it made any sense to go in developing these high-resolution numbers. And this was the best high-resolution Raman setup in the world for a while. It's now in physics and engineering. And, I mean, the pieces are gone, but at the time, this was pretty good stuff, I would say.
Okay, if there's no other questions, then I'd like to conclude with the giveaway section of the presentation. So we have this certificate of appreciation for you, Joe. It has the name of the lecture and the date, and the relief has a picture of the bristlecone pine, which is the species with the longest longevity. So I think it's fitting. And it also has a very durable wood, which I think is also fitting, and very twists and turns in its growth habits. So maybe something that's fitting for a long career such as yours.
Oh, well, thank you.
Okay. And the second part of the appreciation is completely recreational. It's from a nearby winery.
Oh, is it you?
Yeah,
Yours?
yeah, right.
Wow, okay.
So please enjoy.
I've heard good things about this wine. I'm sure you can, if you lean on it, you can probably get some.
Right, we have to work for it, like you did say.
Yeah, well, you do. This is
All right, so please join me in thanking Joe again.